Okay, so we've been talking about measuring and how to be precise. And so when we're talking about measuring, there is some level of error that we as humans have and in our confidence in the devices that we're using in order to measure. So what we are talking about today is uncertainties, and these happen in every single measurement, no matter what. Okay, we as humans are less precise than maybe a machine, but still, devices are still with some level of uncertainty. Now, the reason why possibly the measuring device could be a little bit off. Maybe the techniques or the methods of measuring by the scientist or even you, the student, may be a little bit imperfect. The nature of the measurement itself, sometimes observations that have to be taken that change quickly with time. So there's always going to be some level of measurement that's going to be a little bit not exact. And so we take into account this level of uncertainty. Now, uncertainties, when we're talking about uncertainties, we do have to talk about precision. Now, precision in a measurement is how close together a series of measurements are to each other. For example, here you have all of the arrows that are hitting the board in the same area. However, they are nowhere near the actual mark of what you would like to hit on the board. For accuracy, accuracy merely says that how close a measured value is to the accepted value, which is the bullseye in the board. However, you notice that your precision is not always there. So maybe your marks are a little off, but they are hitting the accepted value. Now, if you look at this board with the arrows, this is neither precise nor accurate. You have measurements that are kind of separate from each other and nowhere near the true value. For this next, over here, we have all the measurements that are close together, but not anywhere near the true mark. This is precise, but not accurate. Over here, we have accurate, but not precise. And then, of course, where we need to be, where we would like to be, it's the ideal, is to have our measurements both precise and accurate. So here's my action figure Optimus Prime, and he weighs about 363 grams. Now, what we're going to do is we're going to try 3 different weight scales to test its precision and accuracy to see whether or not we can actually get to this 363 grams. So let's take a look. So we have scale number 1, and notice how scale number 1 has 360, 340, 389, 390. Is this precise? Is this accurate? Is it both? Is it neither? Over here we have scale number 2, 377, 376, 375, 376. A little bit closer. And then scale number 3 has 362, 361, 363, 362. So, looking at these, let's go back to the first scale and let's see what this is. These measurements kind of look like this. They're spread out, but they're not really hitting the mark. So they're not precise and they're not accurate. Over here, you've got your numbers closer together. But remember, the action figure weighed 363 grams. So it's precise, but it's not accurate. Over here, we have scale number 3, 362, 361, 363. Hey, that's how much ours weighs. And 362. So this one is both precise and accurate. Now, uncertainty. Uncertainty is the best estimated value. That is above or below some level. Okay? And so pretty much what you're looking for is when we make a measurement, you're going to make the measurement that is going to be the best estimate plus or minus a small amount. Okay, so let's go ahead and try this. So this is what we call the true value when you take into account the possibility that it could be a little bit above or a little bit below your measurement. So for example, we have 1.23 plus or minus 0.05 grams. This means that the true value falls in between 1.18 and 1.28 grams. All I did was take the 0.05 and you subtract it from 1.23, and that gives you the 1.18. You take the 0.05 grams and you add it to the 1.23, and that gives you the 1.28 grams. So at the least it can be this amount, at the most it could be this amount. So let's take a look at this graduated cylinder. Over here it is inflated so that way you can see a little bit more, and let's take a look. So we have 41, oops, where's my cursor? So I have 40, 41, 42, 43. Remember, we measured down at the bottom of the meniscus. So when we are trying to determine absolute uncertainty for any devices that are called analog, and analog is a non-digital device, okay? We are going to be taking half of the smallest division. So going back over here, we see that each small line is 1 milliliter. So if we take half of the smallest division, half is 0.05, or 0.5, I believe. So the absolute uncertainty is plus or minus 0.5 centimeters cubed, because 0.5 is half of 1 centimeters cubed. And I said milliliters. Milliliters is the same amount in volume as centimeters cubed. So at 43.5, it looks like, plus or minus 0.5 centimeters cubed, this means that the measurement is at least 43 centimeters cubed and at most 44 centimeters cubed. Okay, so this is just allowing you for a little bit of error in your measurement, letting everyone else know that the actual measurement could be somewhere in that range. Now, for determining absolute uncertainty for digital devices, these are more precise, more accurate than when we're using devices that are not digital. So all you need to do is take the same number as the smallest division. So here we have 0.6. Okay, so it's 1 decimal place out. So we have a measurement of 27.6 plus or minus 0.1 degrees Celsius. That means that the measurement can be at least 27.5 degrees Celsius and at most 27.7. Here we have a ruler, and we know that it's like 7.5, 8, 8.1, 8.2. It's a little bit longer than 8.2, but the smallest division we see is 0.1 centimeters. So half of that, because this is an analog device, so remember we take half of the smallest division, which is going to be 0.05 centimeters. So our answer with the measurement would be 8.2, maybe 8.25 plus or minus 0.05 centimeters, which means that the length of the pencil can be either 8.20 centimeters and at most 8.30 centimeters. Did I add that right? Oh, actually it would be, yep, 8.3. Yes, just checking myself. Okay, so reading this digital device right here, we have 335.49, and remember, when this is a digital device, you are going to take the decimal place and the last decimal place, and that will be your area to take for the absolute uncertainty. So we have 335.49. The absolute value will be 335.49 plus or minus, and then remember we go all the way out to the farthest digit. So that would be plus or minus 0.01 grams. Okay, so that's pretty much everything, and just be ready to use this in class next.